This is lecture 14 on the course Calculus of One Variable, and in this lecture we would discuss the notion of bounded sequence. Now this notion, this term boundedness, we have seen for the set theory. We say that the given set is bounded if it has an upper bound and lower bound. So in general, if we can see that mod of every element of that particular set can be made less than or equal to, say, some fixed positive real number. So that concept of boundedness we extend for the sequence also. So in general, we say that the given sequence is bounded if range of the set, if range of the sequence is bounded. Since we know that the range is a set, and since we have the definition of boundedness of a set, we can talk the boundedness in terms of a range. Okay, so now how do we put this mathematically? So how do we say, instead of writing this in terms of range of the sequence, how do we write down this directly, or what does it mean? Okay, so if I have a sequence, some sequence, and if there is a positive real number, then I would see the band minus C to C. Now I say that the given sequence is bounded if I am able to find such C such that all the terms of the sequence lie inside this band, somewhere here. Okay, so that is, say, suppose x1 lies over here, x2 lies over here, x3 lies over here, and even it may lie on the line x4, and this goes on. Okay, so no matter what that C is, even you can find a very small positive C, or you may find a very bigger positive C, but all the terms of the sequence, see, it's not that ultimately I want the terms of the sequence to lie in this band, but all the terms of the sequence should lie in this band, that is from minus C to C. So how do we put this mathematically? So let me produce the definition for a bounded sequence. Definition of bounded sequence. A sequence xn is said to be bounded. A sequence xn of real number is said to be bounded if you are able to produce such C which is positive such that mod of xn is less than or equal to C for each natural number. That is, each term xn can be made less than or equal to can be made less than or equal to C or greater than or equal to minus C. So if I write down this using the definition of modulus, using the property of modulus, this would be same as saying xn lies in the closed interval minus C comma C. Okay, a sequence which is not bounded is said to be unbounded. A sequence xn is said to be unbounded if it is not bounded. Okay, so what basically that means, that sequence, that is, a sequence is unbounded if I'm not able to produce such positive C such that this is true. So that is same as saying, you give me any positive C, I should be able to find a natural number such that for that natural number the corresponding magnitude of the sequence is strictly greater than that C. Okay, if for any C positive there exists a natural number such that mod of xn is strictly greater than C. So that's a definition of unbounded sequence, and that follows from this boundedness, from the definition of bounded sequence. Now let's see some examples of bounded and unbounded sequence. example, okay, so the first example I would take is consider sequence xn defined as xn is equal to 1 by n for each n belongs to n. So will you be able to produce a natural number, will you be able to produce a positive real number such that mod of this sequence can be made less than or equal to that positive real number, or xn lies in between the closed interval negative of that to the positive of that real number? We know that the graph of this sequence approaches, it starts from 1 and it approaches towards the 0. So in fact there are bounds for this sequence. The 1 forms an upper bound and the 0 forms a lower bound. So that this should clearly tell us that the given sequence should lies in between -1 and 1, and hence this 1 acts as a bound for the sequence. And it is very clear to the definition, because we know that each natural number is greater than or equal to 1. Its reciprocal have to be less than or equal to 1. Okay, so we claim in this case that the given sequence is bounded. So what do we observe here? Mod of xn is nothing but mod of 1 by n, which is same as 1 by n, and this is less than or equal to 1 for each natural number, right? The reason here is that n is greater than or equal to 1, and therefore 1 by n has to be less than or equal to 1. So what we have shown is that mod of xn is less than or equal to 1 for each natural number. So have we succeeded in producing a positive real number such that mod of all xn can be made less than or equal to that? So that's 1. Okay. So therefore there exists 1 which is greater than 0 such that mod of xn can be made less than or equal to n for each n belongs to n, and hence we see that 1 is the bound, 1 is c in this case. So hence the sequence xn, which is defined as 1 by n, is bounded. Let me take some more example of bounded sequence. Second one, consider the sequence yn given by yn is equal to 1 by 2 raised to n for each n belongs to n. Now again, this follows from the first example. We know that this 1 by 2 raised to n can be made less than 1 by n for each n, and in fact we have proved this some in the previous lecture somewhere, which says that 2 raised to n is greater than, strictly greater than n for each n belongs to n. So since we know that 2 raised to n is strictly greater than n for each n belongs to n, this implies that 1 by 2 raised to n should be strictly less than 1 by n for each n belongs to n. And now we know that 1 by 2 raised to n is less than 1 by n, which is less than or equal to 1 for each n belongs to n. So is this enough to say that this sequence is bounded? So since we know that 1 by 2 raised to n is positive, so I'll write down this first. So from here I have the relation 1 by 2 raised to n is strictly less than 1 for each n belongs to n. And now since I know that each of this term 1 by 2 raised to n is positive, we can simply write down it as a mod of 1 by 2 raised to n is less than 1 for each n belongs to n. This says that mod of yn is less than 1 for each n belongs to n, and this proves that the sequence yn is bounded and the bound for it is 1. Okay, so therefore we succeeded in producing a positive real number 1 such that for each natural number the magnitude of the sequence is less than or equal to that bound. Okay, and therefore we say that Yn is bounded. Another standard example of a bounded sequence is Zn is equal to minus 1 the whole raised to n. So if you consider this sequence, then this sequence is bounded. Okay, the reason is very clear. You can see that each term of this sequence will either lie on the line plus 1 or minus 1. So if I see the magnitude of this sequence, it's going to be exactly equal to 1. Okay, so we know that mod of Zn is equal to mod of minus 1 the whole raised to n, which is nothing but 1. So in fact, in this case, we have shown that this mod of Zn is exactly equal to 1. This is true for each natural number, and this says that okay, here if I want, I can write down in this way also, because it is true, equality holds, so even I can say it is less than or equal to 1. So this says that 1 is a bound, so that C forms a bound for the sequence. So just like that, 1 is a bound for this sequence, and therefore the sequence is also bounded. So this shows that the sequence Zn is bounded in R. So let's talk now more about unbounded sequence. Examples of unbounded sequence. Now see, the idea that we get is from the graph of the sequence. See, we discuss the nature of the sequence purely through the graph of the sequence. So it is very important to plot the graph and see the nature of the given sequence. Okay, one standard example of unbounded sequence is, consider sequence xn given by xn is equal to n for each natural number. As you can see that as n keeps on increasing, this sequence keeps on approaching towards infinity. So for this kind of sequence, is it possible to produce a bound for them, or is it possible to produce a positive C such that all terms of xn lies in the band minus C to C? So that is definitely not true, because if that was true, then this would directly implies that the set of natural number is bounded above, because all natural number would lie in the interval minus C to C, which is not possible as a set of natural. That's a contradiction. Okay, so this as I made it very clear through the this geometrical view. I would write down the proof for this. I would show that this is unbounded using contradiction. So if possible, xn be bounded. So we expect to get the contradiction. So that is, there exists C positive such that mod of xn is less than or equal to C for each n belongs to n. So that is same as saying mod of xn is okay. I'll write down explicitly what is xn. Mod of n is less than or equal to C for each n belongs to n. Now we know that each natural number is positive, strictly greater than 0, and therefore its mod has to be itself. So is this not a contradiction? This says that C is an upper bound, and therefore we have produced an upper bound for the set of natural numbers. So we have shown that n is bounded above, which contradicts the Archimedean property. Okay, bounded above in R. So why we are getting this contradiction? Because our assumption that xn is bounded above is not true, and therefore we say that xn is unbounded in R. Take a note that whatever property that I'm talking about here about the sequence, that is for a sequence of a real number only, as we are discussing real number systems. Yet another example one can think of. This was one example. Now you can produce a similar example which approaches to infinity as n tends to infinity, or a similar example, so for example minus n, so that approaches to minus infinity as you keep on approaching infinity, and mod of minus n for each n is nothing but n. So again you are going to get the contradiction if you assume that the same sequence is bounded. So even if you multiply say that n by n, then you are going to get much more faster sequence than n square. So that is also unbounded. So that also you can try proving. Another standard example I would like to take is yn defined by 2 raised to n for each n. Okay, so this again is a bounded sequence, because as you keep on increasing the value of n, you see the value of yn keeps on approaching towards infinity. Okay, and therefore this has to be a unbounded sequence. But to prove this, if you assume that this is a bounded sequence, then what will happen? If possible, there exists C positive such that mod of 2 raised to n is less than or equal to C for each n belongs to n. Okay, that is same as saying 2 raised to n is less than or equal to C for each n belongs to n. Fine. Now we know that this 2 raised to n is strictly greater than n, as 2 raised to n is strictly greater than. So this says that n is also less than or equal to C for each n belongs to n. That's a contradiction, because it's just like a similar one. So this actually says that the sequence xn equal to n is also bounded, which is not true. So these are some examples of unbounded sequence. You can construct some more examples to this idea. We will get into some now the theoretical part of this bounded sequence. So that I would treat as theorem 2.7. So this is the seventh theorem in the second chapter. It says that if the given sequence is convergent, then it has to be bounded. Every convergent sequence in R is bounded. Okay, and we would show that the converse of this is not true. So that is, if the sequence is bounded, then it is not convergent. To the above example, you can very easily produce one such example of sequence, and by now you might have it should be clear in your mind too. So let us prove this first, and then get to the remark which says that the bounded sequence is not convergent. Proof. Okay, so we shall begin with any sequence which is convergent. So let xn be a sequence of real number such that xn converges to a fixed point x in R. Okay, so now our task is to find a bound for a sequence xn. So that means we need to show that mod of xn can be made less than or equal to, say, some fixed positive real number. So what I'll do first, I'll have to use the fact that this xn converges to x. So that means for given any epsilon positive, I'm able to find a natural number such that after certain stretch, after that natural number onwards, all xn lies in the interval x minus epsilon comma x plus epsilon. Now since we want some fixed bound, I would be fixing the value of epsilon, and again I would take it positive so that I can get a fixed bound for the sequence. Okay, so what I'll do is that I'll fix epsilon to be 1. You can take any positive real number, not an issue at all for you, which is strictly greater than 0. So since xn converges to x for this epsilon is equal to 1, which is positive, I'm able to produce a natural number, okay, such that for all n greater than or equal to n, we have mod of xn minus x less than or equal to strictly less than epsilon, that is 1. Okay, So this is what we have. So that is, now if I see the bound for xn, so I mean, uh, uh, so if I write down what exactly happening for the sequence xn when n is greater than or equal to n. So thus, I'll call this a star. Thus, for n greater than or equal to n, mod of xn. Now again, I can balance this by this x. So just look at the way the trick I'm applying over here. I'll write down this as xn minus x plus x, so that I get the bound for the sequence xn. Now what I'll do, I'll put this in bracket and apply the triangle inequality, because I know that for n greater than or equal to n, this term mod of xn minus x can be made less than some fixed point. So this is less than or equal to mod of xn minus x plus mod of x, right? And now since I know that this quantity is less than 1, the whole quantity is now less than 1 plus mod of x. This is from star. By the way, this is not true for every natural number. It is true only for those n which are greater than or equal to this capital N. So this is from star. Okay, so what do we see is that we see that mod of xn is strictly less than 1 plus mod of x. And what can you say about this quantity? Is it always greater than 0? So that is one thing we need to observe. See, mod of x can be greater than or equal to 0. If it is equal to 0, then 1 plus mod of x will be equal to 1, which is strictly positive. And if it is strictly greater than 0, then definitely 1 plus mod of x will be strictly greater than 0. So in all the cases, this 1 plus mod of x is the strictly positive quantity. So as we want. Now in this case, but there's a little hitch over here, is that this is true only for those terms which is greater than or equal to n. So we are able to find a bound for those sequence which is which lies after this n. So xn, then xn plus 1, and this goes on. So only this sequence I am able to make less than or equal to some fixed positive quantity. So I'll write down, so that is, we have mod of xn is less than 1 plus mod of x for every n greater than or equal to n. I'll call this as expression 1. This is not at all enough, because we don't know what is happening for x1, x2, and this goes on till say xn minus 1. So the question over here is that, can we find a bound for this? Can we find a bound for this? Okay. So now since these are some finite terms, if I consider mod of x1, mod of x2, and this goes on till mod of xn minus 1, these are only some finite terms starting from 1, 2 till n minus 1. So if you enumerate this would be exactly n minus 1 terms, right? So to get a bound, it's not difficult. You just pick up the maximum element from here. Maximum element from here. So what will happen then, each of this mod of xn will be less than or equal to that maximum in this case. Okay. Now whatever the maximum that you are choosing, again you have to compare with this 1 plus mod of x, because we want to bound for each natural number, for each xn term. So if this 1 plus mod of x itself is greater than every other term over here, then I can consider this as the overall bound. If it is not, then there should be something maximum from this which is dominating this 1 plus mod of x. Okay, so now what I'll do is that I'll choose my C to be maximum of, as I said, to get a bound for remaining xn, maximum of mod of x1, mod of x2, and this goes on till mod of xn minus 1 and 1 plus also mod of x, this quantity. So if I take the maximum among all this quantity, you would see that for all n greater than or equal to n, mod of xn will be less than or equal to that maximum, because it is less than 1 plus mod of x, and I'm choosing the maximum of 1 plus mod of x and the remaining term over here. And if I simply consider mod of x1, mod of x2 till mod of xn minus 1, it's going to have the maximum among that term. So therefore, among this term there is going to be a maximum, and therefore all such term mod of x1, mod of x2 till mod of xn minus 1 is going to be less than or equal to that maximum term. Okay, now I'm going to consider the maximum of this terms and the maximum of this term. So now, since I know that this is positive, strictly greater than 0, and if there is something that from this term that is dominating this term, which is strictly greater than this 1 plus mod of x, then obviously it has to be greater than 0. If at all not, then this would serve as the maximum. Okay, so therefore I can directly say that one thing you can very easy observe that c is strictly greater than 0 as 1 plus mod of x is strictly greater than 0, right? Okay, now each of this so this c work? So that is the question. We know that each of this mod of xi when I varying over 1 to n minus 1 can be made less than or equal to maximum of mod of x1, mod of x2, and this goes on till mod of xn minus 1. So this is for each I belonging to the set 1 to till n minus 1. Okay, so from here now we see you combine 1 and 2. So for n greater than or equal to n, this access the bound, and for n lying in this region, that is the remaining term 1 to till n minus 1, the maximum of this access the bound. And so if I take the maximum of this as well as 1 plus x, that is this, that should be the bound for whole xn. Okay, so therefore mod of xn should be less than or equal to c for n belongs to n, as c is the maximum of all this term mod of x1 till mod of xn minus 1 and 1 plus mod of x. And this says that the given sequence xn is bounded by c. Okay, so that ends a proof of this statement. It's a very important statement in the analysis of a sequence. Now, as I mentioned, the remark, a very important remark, the converse of the above statement is not true. The converse of theorem 2.7 is not true. That is, in general, I cannot say that every bounded sequence is convergent. So we should be able to produce a bounded sequence which is not convergent, and it is clear from the above example. You can take counter example as xn is equal to minus 1 the whole raised to n. This is bounded but not convergent, which is bounded but not convergent. So we have proved that it is bounded as well as we have proved that it is divergent. So with this I end up the session on this bounded sequence. In the next session we would see some more properties of convergence of sequence.